few days ago, we ended here talking about the haloform reaction, and I said that this can be used as a test where this thing eventually falls off and you get a carboxylic ion and a haloform. I talked about chloroform, bromoform. So here's the chloroform, the bromoform. And so what's going to be new today is this iodoform, which is a positive test for some alcohols. And you're saying, I don't see an alcohol anywhere. It's a test for alcohols, or we might say a methyl ketone, and under certain conditions, things like ethanol can be oxidized and put that carbonyl carbon there. So it's used to identify methyl ketones. This thing precipitates out and has a distinct color. Alcohols can give a positive iodoform test, at least ethanol does. Let's just imagine ethanol here under various conditions, like with bleach, which is an oxidizing agent. We can definitely imagine ethanol going to acetaldehyde, and now we have the methyl ketone moiety there, and that's how it becomes a positive test for ethanol. So a yellow solid that will precipitate out of solution. So acid-catalyzed alpha hydrogenation. So here's the alpha carbon, and here's just acetic acid, alpha-bromoacetophenone. Ketones in general undergo an acid-catalyzed halogenation. Acidic halogenation may replace one or more alpha hydrogens depending on how much halogen is used. So if you just want one halogenation, you're going to make this the limiting reactant. So of course here you want to realize, let me just do this first part. All right, so I tried to get to the enolate ion, and then it was protonated. Mechanism of acid-catalyzed halogenation involves attack of the eno form of the ketone on the electrophile halogen molecule. So we got to get to the enol, however we get to that, and we can imagine our lone pair of electrons, a negative charge, or the enol grabs the halogen, that thing jumps out, then eventually that will grab that hydrogen, and so there's the alpha haloketone. Loss of a proton gives the haloketone and a hydrogen halide. Any questions? The Hell-Volhard-Zelinsky, that's a mouthful. HVZ reaction. Carboxylic acid halide. We might recognize this as a way to the phosphorus tribromide would turn alcohols into an alkyl halide. Here we get a alpha-bromoacyl bromide, and then hydrolysis of that bromide, we get to the alpha-bromoacid. So here, butanoic acid, we get a halide here, and on the alpha carbon, hydrolysis of the bromide replaces a hydrogen atom with a bromine atom on the alpha carbon of a carboxylic acid. And we probably don't get our multiple halogenations. So bromine and phosphorus tribromide, then dump in a bunch of water. So I like to think of this as replacing a bromide there, just like this reagent does on an alcohol. And we're going to imagine that being the keto form. And here's our tautomerism. Now we have the enol. The enol form of the acyl bromide serves as a nucleophilic intermediate. So if we want, we can imagine lone pair of electrons, or we can just imagine this grabbing the halide. The first step is the formation of acyl bromide, which enolizes more readily than does the acid. And once we have the enol form, grabs the halide, creates a bromide that grabs the hydrogen, and now we have our alpha-bromoacyl bromide. The enol is nucleophilic, so it attacks bromine to give the alpha-brominated acyl bromide. In the last step of the reaction, the acyl bromide is hydrolyzed by water to give the carboxylic acid. So possibly, for me, the heart of this chapter is alpha carbons have an acidic proton. We can make it come off, then it's a nucleophile, and here straight up looks like SN2, so an alkylation. We could probably also do it with a tosylate. Well, look at this thing. We could make that the nucleophile. To me, we'd get something we didn't want, and it says it's less common. Because the nucleophile has two nucleophilic sites, the oxygen and the carbon, it can react at either of these two sites. But if we have our LDA, our lithium diisopropylamine. We don't want to ever imagine this going on. We want to just imagine pulling off hydrogen from alpha carbon and having a nucleophile and doing our regular nucleophilic things. The reaction takes place primarily at the carbon forming a new carbon-carbon bond. We don't want to worry about this. So, the slide's ears were burning. I just mentioned LDA, lithium diisopropylamine, that strong base we saw 3 lectures ago possibly, pulls this hydrogen off. You want to imagine a lone pair of electrons in that negative charge. It's going to just slam into there and give you this product. LDA forms the enolate. The enolate acts as a nucleophile, and there's our bimolecular substitution. Put this group right there. Enamine formation. So what we're going to do is we're going to go back about 3 chapters and look at the 4. Well, maybe I'm not perfectly queued up. Close enough. In the present chapter we're at, we're using a secondary amine, but I imagine you might have forgot. So here's our aldehyde or ketone, and we're going to be focusing on the chemistry on the alpha carbon. But here is the amine shift base. Now somewhere, I think we probably get it in the amine chapter. Maybe I should have looked for the slide here, but ammonia or a primary amine reacts with a ketone or aldehyde to form an amine. If we have a secondary, we're going to get that amine or amine. I don't know how it's pronounced. Main thing I wanted to look at is the mechanism here. Protonate the oxygen, makes carbonyl carbon, susceptible to nucleophilic attack. That thing goes on there. We imagine acid-catalyzed. So let's make hydroniamine and get our catalyst back. There it is. And now we protonate oxygen. This thing leaves as water, and then water comes, pulls that proton off. So now we got our acid catalyst back. Now just imagine that we had a secondary amine. And so here is a secondary amine. Ketones and aldehydes react with secondary amines to form an enamine. So I imagine similar type mechanism. We protonate oxygen. This thing slams in there. And eventually we're going to get to something that looks like this. And then you say, that doesn't look too good there. Well, what we're going to do is we're going to push that over, and we won't have our charge. So they don't explain it right at this point. Ketones and aldehydes react with a secondary amine to form an enamine. Now the enamine has a nucleophilic carbon which can be used to attack electrophiles. This thing right here. So secondary amine. Imagine once a carbonyl carbon here, no double bond here. But now that we got it, so right there is a nucleophilic carbon. And this electrostatic potential map shows you with that red color. Highlights a negative electrostatic potential near the carbon atom of a double bond on this thing here. This is the nucleophilic carbon atom of the enamine. Now the whole reason I went through that business before, I was planning this lecture and I was looking at here and here, and I didn't really see it. Here's our carbonyl carbon, here's our secondary amine, here's a secondary carbonyl amine. But I can imagine acid protonating this thing slamming into here, those electrons jumping out, and it looking like this at that point in time. And then these jump back down, and this leaves, and there's no proton on nitrogen. And we have something like this. And here's alpha proton being pulled off, kind of like an elimination reaction. And here's our enamine. Enamine results from the reaction of a ketone or aldehyde with a secondary amine. Bless you. So why do we care about this? Here's our nucleophile. Here is a alky halide. Here is our bimolecular substitution. So interesting enough, we might imagine something like this. If I want to put something right there, I pull out some type of secondary amine. This isn't going to be a pretty drawing. Let me fix it up. And under the right conditions, I form that. And then I do my substitution, put that on. There it's on. And then I hydrolyze this away. And I've added something right there. Now you might be saying, well, I can probably imagine the same thing going LDA, getting to the same spot, right? Well, we saw in that previous slide that we have a resonance form of this. Imagine that jumping in there. So if we went this route, there'd be trace amounts of this, maybe we'd mostly get that. Maybe this is a way to circumvent that. Enamines displace halides from reactive alkyl halides, giving an alkylated amine salts. The alkylated amine salt can be hydrolyzed to the ketone under acidic conditions. Acylation of enamines. Here's our enamine, here's acyl chloride. Imagine this being the business end. Slam that into there. Here's an intermediate. Now we have an acyl enamine salt. Hydrolyze it, and we've acylated the alpha position. Enamine reacts with the acyl halide, forming an acyl enamine salt. Hydrolysis of the enamine salt produces the beta diol ketone as the final product. So when I think about alpha, the hydrogens, I think chapter 23 is all on this thing here. We'll probably end the semester with this final concept. Condensation of ketones and aldehydes. Condensations combine two or more molecules, often with the loss of a small molecule such as water or an alcohol. The aldol condensation is the addition of an enolate ion to another carbonyl group. It occurs under basic conditions. So aldehyde or ketone, let's just imagine two ketones. Here's our alpha carbon, and we have an alpha hydrogen, so base, and pull that off, and then that can slam into another carbonyl carbon. So we've done that there. There is the aldol product. If we heat it, we basically can probably imagine this thing being protonated and being a good leaving group and form our double bond right there. Under basic conditions, the aldol condensation involves the nucleophilic addition of one enolate ion to another carbonyl group. When the reaction is carried out at low temperatures, the hydroxycarbonyl compound can be isolated. You can bottle this up, purify it. If we heat it, we dehydrate the aldol product to the alpha beta unsaturated compound. Alpha beta unsaturated compound. So it looks a lot like our LDA chemistry. Alpha hydrogens are acidic, pulled it off base. Now we have a nucleophile. We have this resonance structure. During step one, the base removes the alpha proton, forming the enolate ion. The enolate ion has a nucleophilic alpha carbon. I like the lone pair of electrons. Slams into the other carbonyl carbon. The enolate attacks carbonyl carbon of a second molecule of carbonyl compound. Protonation of the alkoxide gives the aldo product. There's our aldo product. And you might imagine we're under basic conditions. Maybe alcohol was our solvent. We don't care. And that's all of